first, always. Yes, because if I don't plug it in, I don't know what I'm facing. I have 7 indeterminate cases. I have a no hope case. I have all sorts and a number, right? Good. So when we plug in infinity, first we have to plug in infinity here, and then we apply natural log to that answer. So first we apply infinity, or we apply the square root of x to infinity. Where is that going?
To infinity.
Excellent. So now the question is natural log of infinity. Where is natural log of infinity going?
To infinity.
Yes. Please, please remember the graph of natural log. Always. This is the graph of natural log. So when x approaches infinity, natural log approaches infinity. Awesome. So the numerator goes to infinity. What about the denominator?
Infinity.
That's it. Perfect. L'Hopital's rule. L'Hopital's rule, 0 over 0 or infinity over infinity. Good. Excellent. So can anyone help us differentiate? Let's start with the denominator because that's the easiest. Can anyone differentiate the denominator for us?
That's 2x.
That's it. Awesome. Let's differentiate natural log of the square root of x. Can anyone help with natural log of the square root of x?
1 over square root of x times 1 over 2 times square root of x.
Exactly. Awesome. Very good. So 1 over the square root of x. So natural log of a function is 1 over that function times the function prime, which is 1 over 2 the square root of x. Awesome. Great job. So let me write the formula one more time for everyone. So the square root of x, 1 over the square root of x times the square root of x prime. And the square root of x prime is 1 over 2 the square root of x. Jump over all this. The numerator now, 1 over the square root of x times 1 over 2 the square root of x changes into 1 over 2x. How do I know? The square root of x times the square root of x is x. You can say the square root of x and the square root of x is the square root of x squared, which is the absolute value. But yes, but see what happens here. It goes to positive infinity. Over 2x. But this is 2x over 1, and I have to flip it. So the limit is now, as x approaches infinity, 1 over 2x times 1 over 2x is 1 over 4x squared. 1 over 2x times 1 over 2x. 2 times 2 is 4. X times x is x squared. What is the answer now? Where is the numerator going? Where is the numerator going?
To 1.
Exactly. Where is the denominator going?
To infinity.
Perfect. So I have a pie and I want to share it with everyone on the planet. When I get to your door, how much is left from that pie?
A very tiny amount.
Excellent. So the limit as x approaches infinity is 0. Means y equals 0 is a horizontal asymptote at infinity only. So as x approaches infinity, the function gets closer and closer, closer and closer, closer and closer to 0, which means y equals 0 is a horizontal asymptote. Any questions, anyone? Okay, let's see if we want anything else before we move on to other types of problems. Other preferences here on ratios.
Can we do a trig one?
Yes, please choose anything you want.
What about 29?
29 it is. So we have limit as x approaches 0 from hyperbolic tangent over tangent x. Good. Great job. Okay, so remember, let's talk a little bit, let me refresh your memory a little bit about hyperbolic tangent. Hyperbolic tangent x, of course, is hyperbolic sine over hyperbolic cosine. And if you remember, this is e to the x minus e to negative x over 2, and this one is e to the x but plus e to negative x over 2. And of course, the 2's when I flip go away. And what happens here is when x approaches 0, this is 1 minus 1. So this will be 0. And this is 1 plus 1. So this will be 2. So this is 0. In other words, so as x approaches 0, hyperbolic tangent approaches 0. So the numerator is 0, and thus the denominator is also 0. So I was showing you this analysis to show you or to prove to you that hyperbolic tangent, when x approaches 0, it will also approach 0 like tangent, by symbol. Tangent, not hyperbolic. So we're again in the situation in which we can freely apply L'Hopital's rule, a limit, a function, and preliminary 0 over 0 or infinity over infinity. So all we need to do is just write limit as x approaches 0 and differentiate tangent. If you remember, when you differentiate hyperbolic tangent, we have hyperbolic. I didn't mean that. The power has to be after h, not before h. I'll have to erase that. And this is secant squared x. So now, when x approaches 0, secant squared is 1 over cosine, so it's 1. So the denominator here will be 1. But now, again, how do I determine this? Well, it's the same idea. So hyperbolic secant is 1 over hyperbolic cosine. And when I plug in 1 in it, when I plug in 0 in it, I get 1. So I have to plug in 0 in here. But we already did. And we got 2. So we just did this. So 1 over, so hyperbolic cosine approaches 2. So then hyperbolic secant will approach 1 over 2. And we have to square it. So it's 1 over 4. So the final answer is 1 over 4 over 1, which is 1 over 4. If you think that this was too fast, I will repeat it gladly.
Are there any more with hyperbolic that we could maybe try?
We can find more. So So hyperbolic tangent. So hyperbolic cosine e to the x plus e to negative x over 2. I forgot this 2 here. Sorry about that. I deleted it. So that's so so this is over 4. So it's 4 at the top. So sorry. So it is just 1. So don't forget this. So it's 2, but it's 2 over 2. So when I square it, it has to be 1. So it's just 1. Let me show this one more time. So because I think I confused you. Let me just do this one more time. Just the calculation with this at the end. So we're calculating this again because I want to write it down for you. And this was too fast. So we are here with the limit as x approaches 0 from hyperbolic secant squared over secant squared x. Okay, so secant squared x we already know. So secant squared x is 1 over cosine squared x. So when x approaches 0, cosine approaches 1. 1 over 1 is 1. So the denominator is very clearly 1. But now I want to show this hyperbolic secant squared one more time. So hyperbolic cosine x equals e to the x minus e to negative x divided by 2. If we plug in 0 as x approaches 0, this, so this is 1 plus 1 over, so it's 2 over 2. So this is 1. Now hyperbolic secant squared, so secant hyperbolic, I still put that square there, is 1 over hyperbolic cosine squared. But this is 1, so then 1 over 1 would be 1. So the top and the bottom are 1. Better to simplify from the beginning and we don't have to do anything else. So coming back here, it is 4 over 4, which is 1. Yes, so I'm going to go back to the book and please choose anything else. Any questions on this? So please, Amanda, see if you want to look at something else. There is a hyperbolic sign if you want over there.
We can try that one.
You want to try 28? Good. 28. In 28, we have limit, again, as x approaches 0, from hyperbolic sine x minus x divided by x to the third. Good. When we determine a limit, we have to plug it in first, because we have several situations. We have 7 indeterminate cases. We have the case of no hope, and we also have a case in which the answer is 1/3, and we're done. So hyperbolic sign, when we plug in 0, if you remember, we got 0. So 0 minus 0 is 0, and 0 in the denominator. It's a very lucky case, because 0 over 0 allows us to use L'Hopital's rule directly. There is no manipulation. There is no need to do anything else. Okay. So then we have limit as x approaches 0. Can anyone differentiate the easy one, x cubed, and I'll put it here.
3x squared.
Good. So now when we differentiate sine, we get cosine, hyperbolic, and minus 1. Okay, so now I have to try again, and we just determined that cosine, hyperbolic cosine at 0 is 1. So 1 minus 1 is 0, and the denominator is also 0. Fine, still L'Hopital's rule. Let's continue. So we have limit as x approaches 0. Can anyone differentiate the denominator first? Let's differentiate the
6x.
denominator. So it's 6x, perfect. Remember, when we differentiate hyperbolic cosine, the sign is not negative, but positive. So I have hyperbolic sine x divided by 6x. Perfect. Okay, now, hyperbolic sine at 0 is still 0. And the denominator is still 0. Fine, L'Hopital's rule, we move on. Again, can anyone differentiate the denominator?
Six.
Perfect. And we know that when we differentiate hyperbolic sine, there is no sign change. Of course, these are for sine anyway, it wouldn't have been. And now when x approaches 0, we already know hyperbolic cosine when x approaches 0, the answer is 1. So the answer will be finally 1 over 6. Any questions on this problem? Anyone? Okay. So I think we know where we're coming from when it comes to ratios for now. We can go back and do more when we review or some other time or later on today. So the ratios, we have an idea. Okay, I would like now to look at a product. So we're moving on to products. And I would like to continue with that product. So I can put this aside or recycle it that we had last time that I said, let's wait. And then we choose other products. And I think I'm on page 5. Yes, I'm on page 5. So it was limit as x approaches 0 from the right, from x squared natural log x. And now I can put this aside and forget about it. Good. So we already got it started, but let's talk about it again.
Can you switch back over?
Oh, of course. So sorry. So this was from a graph from last time. So we start by identify where each piece is going. So when x approaches 0 from the right, where will x squared go?
To 0?
Absolutely. Perfect. So let's forget about this. When x approaches 0 from the right, where will natural log go? And remember the graph. So we don't have to think. We just remember the graph and we know where it's going.
Negative infinity?
Negative infinity indeed. The sign is not important. So this is the product. So back to my first page here. No, my second page actually. So we've seen enough of these. We'll go back. And now we're here. We've seen this. Many situations are just rationalizing or some other situation. They're rarely, in differences, we rarely use L'Hopital's rule. Because we can use L'Hopital's rule only if I can change this into one of these two. Kind of impossible. But can I change this into one of these two? Very easily. Very easily. Let's see how we do it. So the product, every time we encounter a product in a limit, the answer is algebraic manipulation. I changed the function, but the outlook of the function, not the function itself. Okay? So let's see how we do that. I will continue here and write limit as x approaches 0 from the right. We never ever touch natural log. Leave it alone, because if you bring it to the denominator with power -1, it's going to be a mess. So we never touch that. So leave the natural log alone. And here's what I'm going to do. So I changed this part of the function into 1 over x squared, because when I divide, I have to flip the denominator, and I get that. So in other words, x squared is the same with 1 over x to -2, or 1 over x squared. 1 over x squared. X to -2 is 1 over x squared, which if I divide, I get back to this. So the algebraic manipulation that I'm talking about in this function is keeping natural log alone and changing x squared into 1 over x squared. Now I'm in business. How come? Because this is still going to infinity, or negative infinity. It's not important. The sign is not important. And this one, I know the graph. I know the graph of 1 over x, which is this. But 1 over x squared is this. This is the graph of 1 over x squared. So when x approaches infinity, when x approaches 0 from the right, where is the function going? X approaches 0 from the right. The function is approaching
Infinity.
That's it. That's all I wanted. So what have we learned here? That the product can be easily changed into a ratio, if it's possible. Because the ratio may be, I don't know. But as long as it's infinity over infinity or 0 over 0,